Good morning dear students, welcome back. I am your physics professor Dr. Nagaraj. So teaching lasers for engineering students, especially for students under VTU. So this is the third video in the series. In the previous video we were talking about Einstein's theory. In Einstein's theory of A and B coefficient, we derived the expression for energy density. It is of this form: U gamma is equal to A divided by B. It is because of A divided by, it is also called as theory of A and B coefficients into e to the power of h nu by kt minus 1. So this is the expression for radiation density. This is also theory of laser. This is also Einstein's A and B coefficient. So from this equation we drew some conclusions like B12 is equal to B21. That means absorption rate is equal to stimulated emission rate, and also we proved that A divided by B is equal to 8 pi h nu cube divided by c cube. That means as frequency of the incident radiation increases, spontaneous emission increases, not the stimulated emission increases. That clearly shows that there must be one more level called metastable level. So all these things we have discussed in detail in the previous video. Now with this introduction, I move on to the next topic, that is today's topic. Now it is requirements and conditions. So first I will talk about conditions and then requirements. So what are the conditions for lasing action? So this is also one of the important questions, conditions for lasing action. Dear students, actually there are three conditions for getting the lasing action. First of all, what is laser? It is nothing but stimulated emission. It is nothing but population inversion. It is nothing but more and more photons. So all these things are associated with laser. So laser is a highly monochromatic light. In order to get laser, we should have stimulated emission. For stimulated emission, there must be metastable state. So first and foremost requirement is metastable state. Without metastable state, you cannot get the lasing action at all. So metastable state requirement. So you just give one or two line explanation. What is metastable state? It is an energy level whose lifespan expands, or lifespan is somewhere between 10 power minus 3 to minus 5 second. So compared to ground state, it is unstable. Compared to excited state, it is metastable. Sorry, it is stable. So this is ground state, this is excited state, this is metastable state. So when you kick the atoms, they will come here and the number keeps on increasing. Finally they will come down to the ground state. So metastable state is one where we have this stability concept. So important condition is availability of the metastable state. Next, just by having metastable state, we cannot get the lasing action. Bari metastable state idre saku laser barodilla. First of all, that metastable state should be populated. That means there must be more number of atoms in the metastable state. That means I have to achieve what is called population inversion. So this is population inversion. This is the second requirement. Again you write one or two lines. What all you have to write? Normally in the ground state there are more atoms, that is N1, than the excited state or metastable state. Let us say N2. So N1 is always greater than N2. This is the normal condition. But normal condition we don't want. We want abnormal condition. That means N2 should be greater than N1. This abnormal situation is known as population inversion. This much if you write, that is sufficient. So that is the second requirement. Third requirement, third condition, not requirement, third condition. Third condition, you know, what is the third condition? Okay, we have metastable state. We need to increase the population here. Then how to increase the population? That is the question. How to increase the population? How to make N2 greater than N1? Because all the atoms will be in the ground state. To begin with, there will be atoms in the ground state. I want to take them to this state. So for that, what I have to do? Yes, you are correct. I have to pump them. So next is pumping process. So first availability of metastable state. Next, that metastable state should be thickly populated. For population, for that to achieve population, I have to pump. Therefore next requirement is pumping process. So these are the three important conditions for lasing action. So what is pumping process? By means of energy energy by means of incident energy, ground state atoms are taken to higher level. Ground state atoms are kicked to higher level. Thereby I can achieve the lasing action. So third and final condition is pumping process. In pumping process, atoms those who are in the ground state are incident with or supplied with external energy. As a result, they go to higher level and their number keeps on increasing. Later on they will come to the metastable level. Immediately they will come, and here atoms or molecules or electrons will stay for a while. Once population increases to maximum extent, they will jump down by means of stimulated emission. Thereby I get laser. So this is the brief explanation of lasing action. So repeat, for achieving lasing action, to get the laser we need to satisfy three conditions. Number one, metastable state, availability of metastable state. Number two, population inversion. Number three, pumping process. For each you can expect 2 marks. So 2 plus 2 plus 2, 6 marks. I hope you followed this. So condition part is over. Now I move on to the next one. Condition admele. After condition, next comes the heading requirements. So many students, they get confused between conditions and requirements. What are the conditions? What are the conditions? I repeat, availability of metastable state, and of course population inversion, and then pumping process. So this is condition part. Now coming to requirement, I told you in the beginning, not in all the elements there are metastable state. Metastable states ella elements allu irodilla. They are available only in few elements, some selected elements. So therefore, while choosing the material for lasing action, we have to be very careful. Look for the elements where there are metastable states. For example, if you take ruby laser, ruby bandbittu, it is chemical symbol of ruby is Al2O3 Cr2O3. Even though there is aluminum, oxygen, chromium and oxygen, not all of them are having metastable state configuration. It is only chromium which is having metastable state configuration. So element or the medium or the cavity or the substance, ಯಾವುದಾದರೂ ಕರಿಬಹುದು, where you have this metastable state configuration, that is known as active medium. So now comes the first requirement, availability of metastable state, or the substance offering metastable state, or the medium offering the metastable state, which is called active medium. So first and foremost requirement, condition ಬಂದು metastable state ಇರಬೇಕು. ರಿಕ್ವೈರ್ಮೆಂಟ್ ಏನು? ಮೆಟಾಸ್ಟೇಬಲ್ ಸ್ಟೇಟ್ ಇರ್ತಕ್ಕಂಥ ಎಲಿಮೆಂಟ್ ರಿಕ್ವೈರ್ಮೆಂಟ್. ಕಂಡೀಷನ್ ಈಸ್ ಅವೈಲಬಿಲಿಟಿ ಆಫ್ ಮೆಟಾಸ್ಟೇಬಲ್ ಸ್ಟೇಟ್. ರಿಕ್ವೈರ್ಮೆಂಟ್ ಮೀನ್ಸ್ such type of material is required. So here if you just take aluminum, it is not sufficient. Aluminum along with chromium is going to be a lasing, suitable for lasing action. So I call chromium as active medium. So first requirement ಏನು? Availability of metastable state in a material. That material is called active medium. So active medium is required. Understood? Yes sir, active medium is required. Next, okay, I said population inversion needs to be achieved. For that I have to pump the atoms or I have to pump the electrons anta. So for pumping, what to do? I have to supply the energy. So therefore I need source of energy, source for pumping. That means you have to lift the atoms. To lift the atoms you have to supply energy. Therefore there must be pumping source. So next requirement is pumping source. This pumping source is obviously energy source. It is obviously energy source. It can be any source. It can be light source or electrical source or chemical source. That means pumping can be achieved by means of light energy, optical energy, electrical energy, even chemical energy also. Based on that, we name it as optical pumping, electrical pumping and chemical pumping. There is one more type of pumping called current injection injection pumping. By applying large current, we can make more atoms to be available. We can make more atoms to go to metastable state. So what type of energy you are using, based on that we name the pumping process. But in general, for pumping the atoms or electrons, we need a source. Therefore availability of the pumping source is another requirement. So if the pumping is done by means of optical energy, then it is called as optical pumping. Optical pumping. So based on the source what you are using, we name them. Sometimes we use high voltage, high electric current we use, so that is called electrical pumping. Electrical pumping. Sometimes we pass high current, high voltage aitidu, high current also we use, that is called current injection. It is something like injecting something. When you inject, no, we call it as injection. Similarly, by means of current we are injecting the charges, we are injecting the atoms into the metastable state. That I will explain next. So current injection, that is also one of the pumping mechanism. Sometimes we use chemical energy. Through chemical reactions also we can kick atoms, that is called chemical pumping. So these are all various pumping mechanisms. But look at this, there is no temperature. Thermal pumping is not mentioned here. That means by means of heating the substance, we cannot take sufficient atoms to the metastable state. See, atoms will be in the ground state. If you heat this, definitely atoms will go to higher level, but not as per our expectations. In order to take more atoms to the higher level, that means in order to make N2 greater than N1, I have to heat it to several thousands of Kelvin, maybe 10 to the power of 5, 10 to the power of 6 Kelvin. ಆ ಥರ ಸಿಕ್ಕಾಪಟ್ಟೆ ಹೀಟ್ ಮಾಡಬೇಕು. Thermal pumping is not possible, because if you heat to such a high temperature, substance may not exist. So therefore thermal pumping is not allowed. Okay, anyway, there are various pumping mechanisms: optical pumping, electrical pumping, current injection, chemical pumping. Depending upon type of the laser, we make use of it. For example, first laser, ruby laser, it had a ruby crystal. First laser which was designed by T.H. Maiman, it was consisting of a ruby rod. In this ruby rod, okay, chromium atoms were there here and there, and this ruby rod is surrounded by helical flash lamp. So on the tube anna ಸುತ್ತಿರ್ತಾರೆ ಇದಕ್ಕೆ helical flash. Suppose if this is a ruby rod, helical flash lamp, tube is wounded. So this tube is finally connected to battery, connected to supply, power supply. When you switch on the power supply, this tube gives intense flash. Sudden ಆಗಿ ನೀವು ಫೋಟೋ ಕ್ಲಿಕ್ ಮಾಡಿದಾಗ ಫ್ಲಾಶ್ ಬರುತ್ತಲ್ವಾ, like that sudden flash it gives. Because of such a intense flash, chromium atoms are excited, then lasing action takes place. So that is nothing but optical pumping. So like that, depending upon type of the laser, we use different pumping mechanisms. This is actually solid laser, because the ruby crystal is a solid material, so therefore it is called solid laser. Sometimes we use gases also. For example, helium neon. Helium neon is a gas taken in a container. Okay, it is gas, helium neon gas, and helium neon gas is connected to high voltage power supply, and when you switch on the power supply, helium and neon gases are ionized. This is called electric pumping. Okay, so electric pumping is suitable for gas lasers. Like that, chemical pumping is suitable for liquid lasers. So ee tara different types of lasers are there depending on the medium. If the active medium is solid, we call it a solid laser. If the active medium is liquid, we call it as liquid laser. If the active medium is gaseous, we call it as gas laser. So depending on the nature of the medium, we adopt different pumping mechanisms. I hope you're following. And there is one more type of laser, that is called semiconductor laser, that I will explain later on. Of course, it is also solid laser only. So if active medium is a semiconductor, then it is called a semiconductor laser. So this is about the second requirement, that is pumping source. So in order to pump atoms to higher level, we need a source, and there are different sources: optical source, electrical source, electric current source, or chemical source. Accordingly, we name them as optical pumping, electrical pumping, current injection, chemical pumping. Got it? No? So with this, I move on to third requirement. Third requirement is very important. Follow carefully. I write third requirement. It is nothing but resonance cavity. What is resonance cavity? That I will explain in the next slide. I need to draw diagram. So resonance cavity. Dear students, follow carefully. This is ruby laser. Let us say this is ruby laser, one ruby rod, and it is surrounded by helical flash lamp, which I already showed in the previous slide, but I write it once again. This is a helical flash lamp. Okay, it is like this. Okay, so now when you connect this to battery and you shine the light, chromium atoms are excited. Chromium atoms are excited from lower level to higher level. They come to metastable level. From there they come to ground level. Laser is emitted. So this is a brief mechanism. Similarly, somewhere here also chromium atoms go there, come here, and then laser is emitted. So along the length and breadth I get different laser pulses. Okay, all these laser pulses are traveling in one direction and they collect. Okay, and they should come back. So like this, by going to and fro, the number of photons keeps on increasing. That means the photon which is going like this should return back like that. So for that to happen, and the photons akade hogi ikade barlike, in order to go that side and this side, I make them to travel back, I make them to reflect back. Got it? Why, sir? Answer is very simple. Why they have to come back? Let me draw one more diagram here. See, I am very interesting. I want to make it more interesting by drawing diagrams. This is a ruby rod. Okay. Well, somewhere here one chromium atom is going to higher level. From there it is coming to metastable and then coming down, and laser is emitted. Meanwhile, this process not yet completed. It is on the way. So this photon cannot wait for it. It will proceed and it will arrive somewhere here. So this is already emitted photon. So these two will join together, and it has to take even this photon also into account. That means that photon should come back. So it goes there. See whether photon is available here or not. So it is not yet ready. So it will go there and comes back. For example, you will go to your friend's house. Okay, you call friend number 1 and then go to friend number 2 house. He says, wait man, I am not ready, give me 5 minutes time. So what you will do, you go to friend number 3's house and then you come back and collect friend number 2 also. So like this, gathering more number of friends is very important. Similarly, gathering more photons is very important. For that to happen, that photon should suffer reflection here. That means this surface should act like a mirror. It should act like a mirror. Not only there, even here also, because it is going there reflecting. Both the ends should act like mirrors. So as a result, what happens? Now I erase this portion. Only whatever is happening inside I will write. So inside now, initially 1 photon, later on 2 photons, later on 3 photons. Okay. So like this, number is increasing, and then while coming back, one more, like one more. Okay, like this I should increase the number of photons. So photons number keeps on increasing. For that to happen, both the ends should be parallel, and they should act like mirrors. Okay, so once the number increases to maximum extent, and finally they will come out from one of the side. For coming from one of the side, there must be small opening here. That means this side should not be completely polished, it should not be completely silvered. There must be small opening, so that from this opening laser light will come out. It acts like a window or a small exit. Okay, suppose if both the sides are fully silvered, it keeps on traveling to and fro, it cannot come out at all. In order to come out of the cavity, there must be small opening. So what I mean to say, the whole active medium should be polished both the sides and silvered such a way that one side is completely silvered, other side is partially silvered. That kind of region, that means this side is partially silvered, this side is completely silvered. So this is a complete mirror, this is partial mirror. So this portion is called resonating or resonance cavity. Why it is called resonance cavity? Because photons, while traveling to and fro, they combine together, they match together, and the number keeps on increasing. Since the number continuously increases, we also call this resonance cavity as gain region or gain medium. So we are going to gain the laser. In fact, this is the point where laser pulse converts into laser beam. Till now it was in the form of photon. Photons are now getting converted into waves. And dear students, remember, length of the resonance cavity L should be n times lambda divided by 2, where lambda is the wavelength of the emitted laser. Because if you, and of course n is equal to an integer 1, 2, 3, etc. Lambda is the wavelength of the laser beam, wavelength of laser. Okay, wavelength, sorry. Okay, so this is about 3 requirements. Number 1, there must be active medium which offer metastable state. Number 2, there must be pumping source which will kick the atoms from lower level to higher level. Number 3, there must be mirror arrangement on both the sides. One of the mirror is partially silvered, the other one is completely silvered. Okay, and this resonance cavity is also called as gain medium. Well, this is about the requirements, conditions and requirements. Even conditions and requirements also you can expect for one full question, that is for 10 marks. Conditions maybe 5 marks, requirements maybe 5 marks. In some colleges they take only conditions, only requirements. Sometimes they ask only conditions, sometimes they ask only requirements. Okay, example for active medium, you can give chromium as the example, helium, neon as the example, carbon dioxide as the example. These are all active mediums where you can find the metastable state configuration. All these details are available in the notes which I have given in the description box. Okay, well, with this now I move on to construction and working of one laser, that is semiconductor laser. I told you, there is a separate type of laser called semiconductor laser. Sorry. Semiconductor laser. What is this semiconductor laser? What are the specialities of semiconductor laser, where it is used, and how semiconductor laser is constructed and working? I tell you, semiconductor laser is a low power laser and cheap, availably cheap laser, cost is less, and it is very small, compact laser. You can have even in your pen also. You might have seen nowadays in key bunch laser they use. China Bazaar, or even in some festivals or exhibitions, you will see that red color, green color coming out from a pen. That is laser only. It is made up of semiconductor laser. And these semiconductor lasers are used in eye surgery, used in defense for laser range finder, and these semiconductor lasers are used in printer, a laser printer anta karitevala. There we use semiconductor laser only. And these semiconductor lasers are made up of compound semiconductors. Sir, what is this compound semiconductor? We know intrinsic semiconductor. Yes, you are correct. You know intrinsic. Intrinsic means pure form of the semiconductor. Intrinsic semiconductor. And we know extrinsic semiconductor. So what is this compound semiconductor? No, I will explain. Intrinsic semiconductor means pure form, germanium or silicon, etc. Extrinsic means germanium with some impurity like phosphorus or some aluminium or some arsenic or some indium, etc. Depending upon the impurity, it will be either P type or N type. If you add trivalent, it is P type. If you add pentavalent, it is N type. Okay, but see, sometimes what we do, we don't consider germanium and silicon, we consider gallium. Actually, it is a trivalent impurity. We consider arsenic, it is a pentavalent impurity, and we combine them together. That gives you gallium arsenide. This is known as compound semiconductor. It is neither pure nor impure. It is a combination of two impurities. The two in the equal ratio, 50-50 we take. And this gallium arsenide, when it is combined with zinc, we get P type. When this gallium arsenide is doped with tellurium, we get N type. So this is a P type semiconductor. This is a N type semiconductor. Okay, so P-type gallium arsenide, N-type gallium arsenide are obtained by doping with zinc and tellurium. And these compound semiconductors are used in the fabrication of semiconductor laser. Even LED also, LED you might have seen, you are using LED. Okay, in your phone also there is one LED. LED is also made up of gallium arsenide or made up of compound semiconductors. Gallium arsenide and phosphorus, gallium arsenide and zinc, gallium arsenide and tellurium finally gives you extrinsic semiconductor. So this is a brief introduction to compound semiconductor. Well, now coming back to diagram. See, dear student, so far you are used to this type of diagram. You are used to this type of diagram. PN junction. So we used to write P and N junctions like this in PUC also. And this is depletion layer. And you know, P is rich in holes. They are represented as plus. So positive charges. Holes are the majority charge carriers in P type. And electrons are the majority charge carriers in N type, like this. Okay. So here we have holes. Here we have holes. Here we have electrons. Okay. And when you form the junction, across the junction up to certain extent, holes and electrons recombine, and therefore in this region there will be no free charges, and this is called depletion. Depleted charges are depleted and nullified, ildangagodu. Mobile charges are depleted, so therefore it is called as depletion region or depletion layer, and it is very, very small, about 10 to the power of minus 6 meter. So it is like that. Okay, now if you connect one end to positive of the battery, other end to negative of the battery, so that P type connected to positive, N type connected to negative, it is called as forward bias. I hope you know all these things, you studied this in PUC. Forward bias. When you do so, then more holes are pushed this side, more electrons are pushed this side, so electrons and holes will move across the junction. Finally there will be current in the circuit. This is the working of PN junction. Now in case of semiconductor device, things are slightly different. Even diagram is also slightly different. The diagram, please follow carefully. Diagram I will write here. See, P type is written like this. P type semiconductor consists of valence band and conduction band. Okay, so this is P type semiconductor, and in P type semiconductor there are holes. I write holes here, so this color I reserve for holes. Okay, and no electrons in the conduction band. Similarly, if you write N-type semiconductor conduction band will be here and valence band will be here, and in N-type semiconductor we have electrons. I use this color for electrons. Okay, yellow color for electrons. Okay, so this is the normal scenario, but here onwards I will write the diagram such a way that this portion I will write only like this. Even this portion I write only like this. Follow carefully. Even here also, I write like this and I write like this. That means this is valence band of N type. This is conduction band of N type. This is conduction band of P type. This is the valence band of P type. Okay na? So I redraw the diagram once again. Here I will draw the diagram. This is very important, dear students. For the diagram itself there are 2 marks and you should understand the diagram. Okay, so P type I write like this. P type is like this. In P type I have holes. So there are plenty of holes here. Okay, next N type I write here. N type I write here. This is N type semiconductor. So P type, N type. This is conduction band of P type. This is conduction band of N type. Sir, why you have not written in same line? Why it is written down little bit? I tell you, N type is connected to negative polarity. Negative polarity means lower potential. So N type energy levels are lowered little bit. Lowered little bit. Maybe this much lowered. This much lowered. Understood? So not in the same line. So this is biased condition. So from here to here I have what is called depletion layer. Okay, I have depletion layer. Well, because of the depletion layer formation, holes will enter from P side to N side. Holes will enter from P side to N side. So some holes will enter into this region. Okay, holes will enter into this region. Similarly, there I have electrons. There I have electrons. Okay, so some of the electrons will enter this region. See what is happening? There are electrons in the upper portion, there are holes in the lower portion. They both are in the junction. They both are in the junction. Clear? Now what happens? Electron will come down, combine with the hole. When electron comes and combines with the hole, energy is emitted in the form of photon. So light is emitted. Suppose if one more atom, electron comes and falls here, we get one more photon. So this way light is emitted by a special type of semiconductor, that is gallium arsenide. And this is what is happening in case of LED. So LED ನಲ್ಲಿ ಇದೇ ಆಗೋದು. So in LED, normal semiconductors are not used, compound semiconductors are used, and they are connected to power supply like this, means forward bias. Because of the forward bias, holes will come from P side to N side, electrons will come from N side to P side, and in the junction region there is a recombination. As a result, photons are emitted. But I don't want normal photons to be emitted. I don't want less number of photons to be emitted. I want more number of photons to be emitted. For more number of photons to be emitted, I should have more number of electrons. ನನಗೆ ಜಾಸ್ತಿ photons ಬೇಕು, ಹಾಗಾಗಿ ಜಾಸ್ತಿ electrons ಇರಬೇಕು, ಅಥವಾ ಜಾಸ್ತಿ holes ಇರಬೇಕು, ಹೆಚ್ಚಿಗೆ holes ಇರಬೇಕು. So I want more number of photons, therefore I should have more electrons here, I should have more holes here. For that, what I have to do? First of all, I have to dope this P side heavily. I have to dope it heavily so that there will be more number of holes. When you dope it heavily, you will get more number of holes. So number of holes increases. Okay, similarly I have to dope this side heavily so that I get more number of electrons. So first requirement, doping concentration should be increased. Second one, you increase the current. When you increase the current, so here you increase the current, then more number of holes will be pushed. Similarly, more number of electrons are pushed, means electrons and holes are injected. Are you getting? No, electrons and holes are injected. Holes are injected from P side, electrons are injected from N side. That means I make more and more holes to enter this region, more and more electrons to enter this region. So I can see ocean of electrons here, cloud of electrons here, and cloud of holes here, See, earlier there were only 3 to 4 holes, 3 to 4 electrons, but because of high doping concentration, because of high current, I got more number of electrons and holes. That means indirectly I increased the population. Got it? Indirectly I increased the population. So population inversion is achieved. Where it is achieved? Not in this region, not in this region, not here, not here, only in this junction region. That is why semiconductor laser is called junction laser, because population inversion is happening in the junction. And one more thing is, there is no metastable state here. I told you just a few minutes back, there must be metastable state for lasing action. But in semiconductor, we don't have metastable state. You can treat the junction itself as the metastable state. It is a region where the whole lasing action is happening. So, illi metastable state illde hodru kuda population jasti aagta ide. So, we are achieving population inversion. How we are achieving population inversion? Number one, by increasing the doping concentration, by adding more and more impurity. Number two, by passing high current. Therefore, I can call this as current injection. I got it. So, because of current injection method, I got more number of photons, more number of electrons there, more number of holes here, and finally they will fall down, giving rise to photons, and all the photons are traveling in the same direction. So, I got thereby laser. Understood? So, this is the mechanism. I repeat once again. This is, okay, I write the diagram once again. This is P side energy level diagram. This is N side energy level diagram. When you combine or when you join, junction is formed. Initially, this is P side. Of course, this is N side. Initially, there will be few holes, even here also one or two, and initially there will be few electrons like this, maybe one or two or three. But because of high current, because of high doping percentage, I get more number of electrons here. So this is going to be ocean of electrons, cloud of electrons. Similarly, this is going to be ocean of holes or cloud of holes. So whole population increases. Finally, the last electron coming from there to here will emit one photon, and that photon is followed by other photons like this. So all the photons will be traveling in the same direction. So they all will have same frequency, same wavelength, same phase, everything same. So this is your laser. So this is the working procedure. Now coming to construction part. Obviously there will be one p-type semiconductor, one p-type semiconductor. This is p-type semiconductor. On the top of it there will be one n-type semiconductor. This is n-type semiconductor. This is sorry. There will be n-type semiconductor. So like this is n-type and this is p-type. Okay, and now it is a cube type. So there are three pairs: first pair, second pair, third pair. So these two pairs are of course this is the junction, this is the main region for me. So this is the active medium called junction. Okay, so this is p-type, this is n-type. The line where they are joined is active medium, that is junction. Okay, so now this face and this face are perpendicular to the junction. These two faces are perpendicular to junction. So these two faces are polished and silvered. Okay, these two faces are, this face and this face are polished and silvered. Why? You know why it is? Because I need what is called resonance cavity. So there should be reflection to and fro. Therefore, these two are polished and silvered. And one surface is 100% polished. This is 100% polished. This is partially polished. So that there will be one opening. From this opening, laser is coming out. So laser is coming out like this. Okay. And the top surface is connected to negative terminal. Top surface is connected to negative terminal of the battery. Bottom surface is connected to positive terminal of the battery, because p-type should be connected to positive, n-type should be connected to negative. Then only it will be in forward bias. So construction is very simple. semiconductor laser consists of p-type and n-type semiconductor sandwiched together to form a junction, and junction is very thin, of course about 10 power minus 6. Two faces perpendicular to junctions are polished and silvered. One surface is partially silvered in order to see that laser finally escape. Other two faces are connected to battery in a forward bias mode, and when you switch on, okay, you can have a switch, and when you switch on, current flows through this, and this is going to happen. So you have to explain along with the diagram. This explanation I already given to you, so please follow carefully. All these details are available in my notes. And okay, finally we have energy gap. Sir, what is energy gap? It is a difference between conduction band and valence band. This is the energy gap. This energy gap is equal to h nu, that is energy gap is equal to hc divided by lambda. So lambda is equal to wavelength of the emitted light. So h is known, c is known, eg is the energy gap. This energy gap is different for different semiconductors. For germanium it is 0.6, for silicon it is 1.1, like that it varies. For gallium arsenide it is 1.43. It varies from material to material. Just by changing the material we can change energy gap. Just by changing the energy gap we can change the wavelength, so thereby we can change the color. So that's why we have red color, blue color, pink color, green color, white color laser also, LEDs are also available. Only difference between LED and laser is LED is working at lower current, less doped semiconductor. Laser is working at high current, heavily doped semiconductor. Otherwise mechanism will be same. Both LED and laser are emitted at the junction itself. So with this I conclude the discussion of construction and working of semiconductor laser. Dear students, this is also one of the important questions. See, in lasers there are so many important questions you can expect. Even next application part, that also very important. There are two applications, namely three applications, namely laser printer, laser barcode reader that you see in shopping malls, and then laser cooling. So I take up this in my next video. So please share my videos with your friends, and also pass your comments, and also subscribe to my channel. So you will get lot of benefit. I am going to solve numerical problems also. I will teach even different modules also. So you stay with me so that I can give maximum from my side. Okay, thank you very much.